Welcome back to Let's Talk About Data. If you're here, you're serious about becoming an AI engineer. Today's episode isn't your average Python tutorial. We're diving into the specific way AI engineers use Python with efficiency, scalability, and machine learning readiness in mind. Hit that subscribe button and turn on notifications because every Tuesday we bring you deep dive AI engineering content. We're diving deep into why Python is more than just a programming language. It's the backbone of scalable, production-ready AI systems. This series goes beyond syntax. It's about building AI with efficiency, reliability, and engineering discipline. Python's power lies in its vast ecosystem. With NumPy, you get lightning-fast numerical computations. Pandas simplifies data manipulation. Scikit-learn makes classical machine learning accessible. And when it comes to deep learning, TensorFlow and PyTorch are the industry standards, with Keras offering an intuitive interface to design neural networks. These tools are production-ready, deeply integrated, and continually evolving to meet the demands of real-world AI development. Python lets you go from prototype to production without switching languages. That's powerful. You can explore a dataset, build a model, deploy it via an API, and monitor performance, all within a unified ecosystem. Whether you're working on image classification, NLP, recommendation systems, or time series forecasting, Python provides robust libraries and community support every step of the way. Tools like TensorFlow Hub and Hugging Face give you access to pre-trained models, so you don't have to reinvent the wheel. But here's the real talk. Python for AI engineering isn't about clever one-liners or quick scripts. It's about modular, maintainable, testable code that scales. As an AI engineer, your job spans the entire machine learning lifecycle, from framing the problem and processing data to deploying and monitoring models in production. You need code that integrates into C/CD pipelines, works seamlessly with APIs, and utilizes GPUs and TPUs for acceleration. And testing isn't optional, it's critical. From input validation to model performance checks, your code must be robust, reproducible, and accountable. Engineering practices like version control, model tracking, code reviews, and ML ops aren't nice to have, they're mandatory. And yes, ethical considerations and bias mitigation are part of your engineering responsibility too. So yes, I'll show you how to use Python libraries. But more importantly, I'll teach you how to engineer AI systems. We're building the habits, the mindset, and the technical muscle that distinguish hobby projects from real-world AI products. This is where coding meets engineering excellence. Now I want to hear from you. What's your biggest Python frustration when working on AI projects? Drop it in the comments, and we'll tackle it together in this series. Because this isn't just about learning Python. This is about becoming a world-class AI engineer. We've talked about why Python is the go-to language for AI. Now it's time to zoom in on the specific Python techniques that elevate you from just writing scripts to building scalable, production-grade AI systems. For AI engineers, it's not just about writing code that runs. It's about writing code that is efficient, scalable, maintainable, and debuggable. Critical traits when you're transitioning from prototyping to real-world deployment. Let's begin with the development environment. Most AI engineers work in Jupyter Notebooks or VS Code. Jupyter is great for quick experimentation and data exploration. VS Code is a versatile editor with powerful Python integration, ideal for large-scale projects. Both environments support debugging, syntax highlighting, and project management, helping you write clean, well-structured code. Imagine you're building a data pipeline for 100 gigabytes of image data. You'll need fast processing, efficient memory usage, and solid error handling. The Python skills you apply here must handle these demands without breaking your system or your sanity. Start with something simple, say, filtering values. A basic for loop works, but in AI workflows, even small inefficiencies can become performance bottlenecks. Here's where list comprehensions shine. They're more compact and often faster because Python can optimize them internally. This technique isn't just cleaner, it's a first step toward writing Pythonic, high-performance code. Next, let's talk structure. Early in a project, you'll use functions to group logic. But as complexity grows, this approach can get messy. Classes allow you to bundle data and behavior together. With object-oriented programming, your code becomes modular, testable, and easier to extend, exactly what you need in sophisticated AI pipelines. Python's dynamic typing gives flexibility, but it can hide bugs that only show up at runtime. That's risky in AI systems where bugs can derail long training cycles. Type hints bring clarity and enable static checks. Adding them helps your IDE catch issues before you even hit run, making your code more robust and easier to debug, especially in large collaborative projects. Sometimes you need to add functionality, like timing a process or logging steps, without altering the core logic of your function. That's where decorators come in. Decorators allow you to extend functionality cleanly and consistently. You'll use them for tasks like performance monitoring or injecting logs, making your code more modular and easier to maintain. Let's face it, print is great for quick debugging. But in production systems, not so much. The logging module is the professional standard. It lets you categorize messages, info, debug, warning, error, and route them to files or external monitoring systems. This makes tracking and debugging much more efficient and scalable. Remember that 100 gigabytes of image data? Trying to load it all at once will crash your memory. Generators solve this problem. Using the yield keyword, you create iterators that return one item at a time. They keep memory usage low and performance high, exactly what you need when handling massive datasets. This is not a nice-to-have. It's a must-have for scalable, memory-efficient AI systems. Let's recap. Today we covered list comprehensions for concise, efficient code, classes for structured, modular design, type hints for reliability and maintainability, decorators for clean feature extensions, logging for professional-grade debugging, generators for memory efficiency. These aren't just Python techniques, they're core engineering practices. Mastering them enables you to build robust, scalable AI applications that perform in the real world. To submit your understanding, download the full Python notebook from today's session. The link is in the description. Practice these techniques, experiment with them, and integrate them into your workflow. Your journey to becoming a professional AI engineer starts here. We've covered the foundational concepts of Python. Now, let's move into what truly powers every AI pipeline, data handling. In real-world scenarios, data is rarely clean. It's often incomplete, inconsistent, and massive in scale. Before any model can learn from it, the data must be properly loaded, cleaned, transformed, and prepared. This stage, often referred to as data wrangling, is where Pandas and NumPy become mission-critical. Why is this stage so vital? Because the quality of your data directly impacts the quality of your models. No matter how complex your architecture is, poor input leads to poor output. Data preparation isn't just a step, it's an iterative cycle that forms the foundation of every machine learning pipeline. For Python-based workflows, two libraries stand out. NumPy is the powerhouse for numerical operations, while Pandas is built specifically for manipulating structured, tabular data. Together, they provide the agility and performance AI engineers need. Let's visualize this. Suppose you want to load a CSV, inspect the structure, and calculate a mean value. On the left, you can see how verbose and error-prone this task becomes with only base Python. On the right, Pandas simplifies the same task to just a few lines. It's readable, efficient, and scalable, everything you want when dealing with large datasets. Let's take it a step further. Real-world data isn't just large, it's also messy. Missing values, inconsistent types, or corrupted entries are common. Pandas makes cleaning this data intuitive. Here, we can see missing values in a column. With just one line of code, we can fill them using the median, drop them, or even replace them with a placeholder. This level of flexibility and control makes Pandas an indispensable tool for every data professional. Now let's shift gears to NumPy, which dominates numerical computing in Python. NumPy arrays are highly efficient, supporting a wide range of mathematical operations. Here's where NumPy shines, its vectorized operations. You can perform element-wise calculations, broadcasting between arrays and matrix operations, all without writing a single loop. This is crucial for both performance and readability in machine learning workflows. Take normalization, for instance. It's a standard pre-processing step to ensure features have zero mean and unit variance. With NumPy, it's a single, elegant line of code. This kind of concise and efficient operation is why NumPy is the go-to for any heavy numerical lifting. So there you have it. Whether it's cleaning tabular data with Pandas or crunching numbers with NumPy, mastering these libraries is non-negotiable for any AI engineer. They form the backbone of all data pre-processing pipelines. If you've ever wrestled with messy data for hours, hit that like button. We've all been there. Don't forget to download the practice notebook linked below. Alright, we've wrangled our data and set the stage for modeling. But before jumping into training, let's talk about structure. As AI engineers, it's not just about making things work, it's about making them maintainable, reusable, and easy to debug. That's where object-oriented programming, or OOP, in Python comes into play. Imagine this, a giant script that loads data, pre-processes it, trains a model, evaluates it, logs results, and maybe even deploys it, all in one file. That's what we call spaghetti code, hard to follow, harder to maintain, and almost impossible to scale. Most of a software project's cost lies in maintenance, often 80% or more. Object-oriented design helps manage that complexity by organizing your code into modular, reusable components. It provides abstractions that hide implementation details and makes adding new features more seamless. That translates into cleaner code, easier collaboration, and fewer bugs. Let's apply this thinking to a real-world AI use case. Training. We'll define a class that handles the training process. Let's call it model trainer. This constructor method, _init_, sets up everything our training process needs: the model, datasets, hyperparameters, and optionally, a logger. This approach clearly defines dependencies and keeps them bundled in a single, reusable object. Now, what behavior should this object have? It should be able to train the model, evaluate it, and log progress. Let's add those methods. By giving each method a single responsibility, we keep things clean and manageable. It's easier to test, debug, and update any part of the workflow independently. Now, let's add real logic to these methods using abstraction. Instead of hard-coding training logic, we assume the model object passed in already knows how to train and evaluate itself. See what we've done here? Our class no longer needs to know the how of training, it just needs the model to follow a consistent interface. Whether it's a scikit-learn model or a Keras neural network, as long as it has fit and evaluate methods, our model trainer can handle it. This kind of abstraction makes the code modular and testable. You can swap models in and out without rewriting the entire training pipeline. Everything from logging to evaluation is self-contained and clear. Let's break down the benefits of this approach. Maintainability. Each component has a clear role. Changes don't ripple across the system. Reusability. The model trainer can be reused for any compatible model. Abstraction. Complex training logic is encapsulated behind simple interfaces. Organization. Your codebase stays modular and scalable, not chaotic and brittle. This is what professional AI development looks like: system-level thinking built on clean, object-oriented code. If you want to explore this further, I've shared a complete model trainer template in the repo linked below. You can plug in your own models, datasets, and hyperparameters and get started right away. So, we've structured our code using NumPy. Great for maintainability. But what happens when your code is clean, yet painfully slow? Let's be honest, Python isn't winning any speed competitions against C++ or Java. And in AI, performance matters. Long training times reduce experimentation speed. Slow inference kills user experience. And massive datasets demand efficiency. Python isn't the fastest, but it can be fast enough if you know how to profile and parallelize. Two pillars of performance optimization in Python are profiling, to identify where your code is slow, and parallelization, to leverage all your available CPU cores. Let's talk about profiling. It's how you find bottlenecks before wasting time on the wrong optimization. Now this analyze_large_dataset function might be part of your pre-processing pipeline. If it's slow, here's how you find out why. cProfile shows how many times each function is called, the total time, and cumulative time. Boom! Process_data_chunk is the bottleneck. Now we know exactly where to focus. Profiling is your performance magnifying glass. Now we optimize. And the fastest way to do that for CPU-bound tasks? Parallelization. By default, Python runs on one core. But your machine likely has 4, 8, even 16. Why not use them? Let's parallelize using concurrent.futures.process, pool executor, Python's high-level API that's clean, efficient, and conceptually similar to Java's executor framework. Each chunk is processed in a separate process on a different CPU core. The result? Huge speedup, especially for heavy computation. For I/O-bound tasks, like file reading or API calls, use thread pool executor instead. So how does this apply to real-world AI? Slow data loading? Profile it. Pre-processing lag? Parallelize it. Inference delay? Optimize it. Libraries like TensorFlow and PyTorch already use threading under the hood. Think tf.data, prefetch, interleave, num_parallel_calls. On a bigger scale, you're distributing training across GPUs or nodes, using data and model parallelism. Parallelism isn't a hack. It's a core principle of scalable AI engineering. So yes, Python isn't the fastest kid on the block. But if you profile intelligently and parallelize strategically, Python becomes more than fast enough for any AI workload. Python isn't the fastest, but it can be fast enough if you know how to profile and parallelize. Want your AI code to fly? Drop a rocket emoji in the comments below. Now that we understand why performance matters and how to optimize it, here's a reality check. You won't be building everything from scratch. The real power of Python and AI comes from its rich ecosystem of libraries. These libraries offer battle-tested, pre-built tools for everything from classic ML algorithms and deep learning frameworks to data visualization, APIs, and model versioning. Knowing which ones matter and why can make or break your workflow. These are the tools you'll reach for again and again. Get familiar with them early. Let's start with scikit-learn, your go-to for traditional machine learning. It's intuitive, efficient, and covers essentials like classification, regression, clustering, and pre-processing. Scikit-learn makes it incredibly easy to go from raw data to model evaluation in minutes. It's perfect for quick prototyping and built on top of NumPy and SciPy. Next, TensorFlow. Originally built by Google, this framework is ideal for production-scale, deep learning, think image recognition, NLP, and more. TensorFlow's Keras API makes building and training neural networks approachable, while still offering robust tools for scalability and optimization under the hood. Then there's PyTorch, developed by Facebook. It's especially popular in research due to its dynamic computation graph and intuitive syntax. Many leading-edge models you read about in research papers are built in PyTorch. It's flexible, transparent, and increasingly used in production too. Visualization is key to understanding your models and data. Matplotlib is the backbone of Python visualization, perfect for static or interactive plots. And for beautiful statistical plots with less effort, use Seaborn, built on Matplotlib and ideal for EDA. Not all insights come from models, some come from smart visualizations. Once your model is trained, how do you make it accessible? That's where APIs come in. While Flask is often used, many teams are switching to fastapi for its speed and simplicity. Fastapi isn't just modern, it's fast, supports async out of the box, and integrates beautifully with Python's typing system. Great for real-time inference. Version control isn't just for code. In real-world AI, your data and models need versioning too. We have Pachyderm, which acts like Git for your data pipeline. An alternative is DVC, Data Version Control. It tracks datasets, models, and experiments right inside your Git repository. Reproducibility is no longer optional, it's essential. Python's AI ecosystem is vast, but these libraries are your foundation. Scikit-learn, TensorFlow, PyTorch, Matplotlib, Seaborn, fastapi, Pachyderm, DVC. Learn them, master them, and build with confidence. Which of these libraries do you find the most intimidating? Drop a comment, and we'll build a tutorial just for you. What a journey today! We began with the critical importance of performance in AI engineering and explored actionable strategies to accelerate your Python code. From there, we walked through the essential Python libraries that power modern AI, from scikit-learn and TensorFlow to PyTorch, Matplotlib, Seaborn, and tools like fastapi and DVC for deploying and versioning your models. These aren't just tools, they're the pillars of your AI toolkit. Mastering Python is a foundational step toward becoming a successful AI engineer. It's the glue that binds your projects together, and these libraries are your building blocks. But if you want to move from practitioner to expert, If you want to design systems, not just use them, you need to understand the principles behind the code. You need the math. That's where we're headed next. In the upcoming episode, we'll explore the mathematical foundations behind machine learning. Don't worry, it won't be overwhelming. We'll break down the core concepts of linear algebra, calculus, and statistics into practical, intuitive lessons you can apply right away. If Python is your toolkit, math is your blueprint. So, don't miss it. Subscribe right now and turn on notifications so you're first in line when the next episode drops. And while you're here, grab your free Python practice workbook. It's linked right below to help you keep sharpening your skills. Keep building. Keep coding. You're already ahead of the curve. See you in the next one.